Hi, in this video, our group will be presenting on our project on text emotion recognition. Let's start with some background information. Social media monitoring, such as sentiment analysis and text emotion recognition, has helped businesses understand their customers. Sentiment analysis categorizes opinions into positive, neutral, and negative, whereas text emotion recognition extends sentiment analysis to extract finer-grained emotions such as happy, sad, angry, etc.
In this section, I will introduce existing techniques. So in the year 2015, a simple naive Bayes classifier using tenfold cross-validation aimed to classify various tweets into emotions such as happiness, sadness, fear, and disgust. They were able to obtain an 83% accuracy, but had a small corpus. They suggested using deeper learning techniques such as support vector machines or k-nearest neighbor in order to obtain better results. Later on in the year 2019, an ensemble classifier of SVM, KNN, and XGBoost, a gradient boosting algorithm used to predict emotions in the International Survey on Emotion, Antecedents, and Reactions, or ICER dataset. They were able to achieve an F-score of 0.85, which at that time was higher than most results. The most recent technique is in 2020, where cross-lingual word embeddings were created from a Hindi corpus of disaster documents labeled with different emotions, and a transfer learning environment of these embeddings between Hindi and English were carried out using a CNN and by Lstm, which obtained an F-score of 0.53. While these managed to obtain very strong results, one common flaw between these methods was a lack of context. Context is incredibly important when it comes to judging emotions within a sentence. As for example, the sentence, "The politician died," could have been preceded by either "I hate this politician" or "I love this politician," meaning that the context of these sentences is incredibly important. So, upcoming, we're going to talk about our project objectives and how we're going to achieve our goal by avoiding the issue of lack of context.
In this project, our objectives is to develop text emotion recognition that is able to capture both local and global information, such as the emotions of words and sentences. In addition, we also aim to develop techniques that is invariant to speakers' writing style and characteristics. In this project, we will be using the two datasets as shown. Moving on to the methods, we first perform general processing to counter the imbalanced dataset problem of crowdflower. We first combined the crowdflower dataset with the emotions for NLP dataset and remove labels with less than 2,000 samples. After this processing step, our dataset consists of the 6 labels as shown.
The first type of model uses LSTM. By having 3 different gates, LSTM can learn longer-term dependencies as compared to RNNs. An overview of the Lstm model architecture for combined data with glove embedding and the hyperparameters are as shown. Next, we extended the idea of LSTM to bidirectional LSTM. Bi-LSTM can capture information forward and backward in time. Combined with attention mechanism, the model is thought to be able to capture additional information. Similarly, an overview of the model architecture for combined data with glove embedding and the hyperparameters used are as shown.
Another method experimented is GRU, which is similar to LSTM but has fewer training parameters and usually trains faster. The model is trained using glove word embedding with the architecture and hyperparameters as shown.
The last method that we used in our project is called XLNet. It is an autoregressive transformer neural network model created in 2019. It has 2 unique features that improve upon existing transformer models like BERT and ELMO. Firstly, the permutation to capture bidirectional context while avoiding independence assumption and the need for artificial corrupting tokens. As noted in the first equation above, our goal is to find a set of parameters theta that ensure the highest probability of the token XZT will appear given the preceding tokens XZ before T. Secondly, the two-stream self-attention mechanism as detailed in the diagram below. That it is to ensure attention to word order and context while solving an issue of positional indexes from previous transformer models. Due to all these factors, XLNet is considered the best model for NLP tasks as of right now. It has a general language understanding evaluation or GLUE score of 90.9, higher than the human average of 87.1. However, XLNet is also computationally expensive, and because of that, I was only able to run 15 epochs with the free GPU time that was allotted to me. With all that said, here are the results of our experiments.
For the discussion part, we will first take a look at the performance of models. For the Crowdflower dataset, Lstm with glove embedding performed the best, having the highest test accuracy of 44.24%, whereas the models without glove embedding and XLNet did not perform as well, as their test accuracy ranged between 30 to 40%. For the combined dataset, the Lstm model with glove embedding once again performed the best, having the highest test accuracy of 60.95% and lowest test loss. Nonetheless, BiLSTM with attention mechanism and XLNet performed almost equally as well, as the test accuracy between Lstm and XLNet differed by only 0.5%. Also, these three models used in the combined dataset outperformed all models trained solely on the Crowdflower dataset, which was a good achievement. Next, for our task, pre-training has shown to be significantly useful by improving overall test accuracy of various models by a substantial amount. For XLNet, this was achieved by using a pre-trained sequence classification model, and for the other models, a pre-trained glove embedding layer. As pre-training is done on large training data or corpus of words, it can generalize well when used on similar problems, which in our case, help better predict emotions from sentences rather than those models trained from scratch. Looking at the dataset quality, similar research done and Kaggle attempts on the Crowdflower dataset also achieve low accuracy of around 30%. Some explanations for these are as such. Firstly, the data is noisy and has more labels compared to other data used in text emotion recognition. Secondly, unconventional tweets such as slangs and improper spelling might make it harder to capture the right emotions. Therefore, the Crowdflower data is determined to be of poor quality, making training on it challenging. While initially combining data was to solve the issue of imbalanced data, here it proved to be useful as another method to better compare our models' performances. All in all, we achieved our project objectives by designing models that fulfill the aims outlined earlier. Firstly, our models were able to capture local and global information not possible in RNNs. Moreover, XLNet was able to be invariant to style and characteristics of speakers. Additionally, we conducted detailed comparison of model performances by combining various models and data. Lstm with glove embedding was deemed to have the best performance among the trained models. In undertaking the project objectives, we also identified the benefit of pre-training and the dataset quality of the Crowdflower dataset. These can serve as useful knowledge and experience for improvements or for future projects. Here are some future improvements that can be undertaken. Firstly, the tuning of hyperparameters and pre-trained layers and models to achieve better test accuracy. Secondly, training XLNet for more epochs given sufficient computation resources. And lastly, using better quality dataset to compare and train our models.